Okay. Any questions before we begin on anything? So last time we just learned about some shortcuts for taking derivatives because, you know, the limit definition can get tedious. We don't want to spend all day computing limits. So yeah, we were able to take the derivatives quickly for more complicated functions, but we still want to extend that even more, which brings us into, yeah, I believe I finished 3.1. So this brings us into 3.3. We're skipping 3.2 for the time being because it's more of an applications-based section. I just want to get through the computational section, like how to find derivatives of various things. So in 3.3, we're going to talk about the product and quotient. Just recall something. Remember that if we're taking the derivative of a sum or difference, that's just the sum or difference of the derivatives themselves. The question is, does a similar thing hold true for products? Quotients, which means you're finding the division of something. That's the question that this section is going to answer. It turns out no. It turns out if there's a multiplication connecting functions here, you can't just put a multiplication there and everything's okay. It's actually not correct. There's one easy way to check. Right? So for example, if I ask you to find the derivative of x squared, what is the answer?
2x.
2x. Okay, so I know that answer based on the power rule. Okay, but what if I did it another way? What if I asked you to find the derivative of x squared by first thinking of it as a product? Let's say x times x. Right? And I ask you, is this the same as saying the derivative of x times the derivative of x? Turns out that obviously is no, right? Because derivative of x is 1, derivative of x is also 1, so this would give you 1 as the answer, which we know is not the answer. So it turns out if I have things multiplying, I can't just differentiate each piece and stick it together. It'll give me the wrong answer. There is no rule like this for products. So now the question is, how would we differentiate a product, right? How do we actually differentiate something when there's a multiplication combining functions? It's not as simple as if there's a plus or minus combining functions. So here's the rule. Suppose my y is a product of two functions, f of x times g of x. Then, this means if I want to find the derivative y prime, I can start to use the limit definition. And as h approaches 0 of, I need to take this function evaluated at x plus h. Minus the function just at x. All over h. Now we do that weird thing that math people like to do. You add 0 in a convenient way to simplify things. Right, like when you're completing the square, that's what you do. So what you're going to do here is I'm going to add and subtract something. That's going to kind of look weird for me to add and subtract in the first place, but you'll see that it works out. In the middle, what I'm going to do is I'm going to subtract f of x times g of x plus h and add f of x times g of x plus h. So I added and subtracted something, so I'm not changing the value of this function. That guy is just 0. And you're like, well, why would you do that? What's up with that, people? What I'm going to do now is I'm actually going to split this into two fractions. Right? I can split into that and this. What's going to happen now? I'm going to have f of x plus h times g of x plus h minus f of x times g of x plus h over h plus f of x times g of x plus h minus f of x times g of x over h. Can we do anything in this first part? You might notice there's a common term. So let's factor that out. Let me put it at the back, just for aesthetic purposes. So I can factor off a g of x plus h. Similarly here, f of x is a common term. I can factor that off. So now, remember we do have product rules for limits and sum rules for limits. So this really gives me the limit as h approaches 0 of f of x plus h minus f of x over h times the limit as h approaches 0 of g of x plus h plus the limit as h approaches 0 of f of x times the limit, because limits distribute across sums and products. We actually mentioned that before. G of x plus h minus g of x over h. What's this guy?
That's the derivative function.
That's the derivative of f. That's f prime of x. What's this guy? Limit as h goes to 0 of g of x plus h. Just g of x. Plug in h equals 0. Plus this guy. Limit as h goes to 0 of f of x. Just f of x, because there is no h there. Times, what's this guy? That's actually the derivative of g. So look at what it ends up being. F prime times g plus f times g prime. This is known as the product.
Wait, before you erase that. No.
Wait, did we have to write this whole thing?
That second thing down there. Yes, there.
Yeah, what about it?
What did you do in that centerpiece?
These, I added and subtracted something. I
Like
basically
what?
added 0. This thing here is 0. So I didn't really do anything technically.
And so you just did this so you can split it?
I did this so I could split it into two things where I see a pattern.
Okay.
Yeah.
Wait, do we have to write all these steps on the end?
No.
Alright.
Summary. If I want to take the derivative of a product, one function times another function, then that will give me the derivative of the first times the second plus the first times the derivative of the second. This is a general rule, and it is known as the product rule. And this you have to memorize. This is called the product rule, and it's used to differentiate products of functions. All right. So if I want to find the derivative of one function times another function, the answer is going to be differentiate one function, leave one function alone, plus leave the first function alone, differentiate the second function. And that's the rule because, I just proved why that had to be the case. That's called the product rule. Use it when you want to differentiate products. Did I write any examples of it? Did I give examples now, or do I want to give examples later? Well, I did some silly examples. I really made more complicated examples later. Let's use this rule to find the derivative of x squared. See if it actually coincides with what we know the answer should be by the power rule. Right? So if I look at this as that, which x times x is x squared, so it should work out. What if I actually did this like the product rule? Meaning I think of this as one function f, that as one function g. Right? Then my f and g, my f would be x, my g would be x, my f prime would be, and my g prime would be what? 1 and 1. So according to this rule, I have to have f prime times g, so that's 1 times x, plus f times g prime, which is x times 1. That ends up being 2x. So it seems to work out. It turns out it will always work out. So I didn't really write any examples, but let me give you some now anyway. So for example, find the derivative of So it turns out individually we know how to differentiate x cubed and we know how to differentiate e to the x. The thing is I'm multiplying them now, right? So this is one other thing you'd have to look out for when you're doing derivatives. Is your function a multiplication of two very different functions? Right? Let's throw another one in here. d y equals x times radical x. So the thing is, I can't just differentiate this and differentiate that and that's your answer. That will end up being wrong. Right? Because it's a product, we have to go through the product rule. So I look at that, I realize it's a product of two different functions. I need to find the derivative of this product. So a, y is equal to x cubed e to the x. This means I know my y prime is going to be. So here, I call one function in the product an f, the other function I call a g. And you can go to one side and write this all down. So you can say f is equal to x cubed, and your g is equal to e to the x. And then you find your f prime, then you find your g prime. So if f is equal to x cubed, what is f prime? 3x squared. And if your g is equal to e to the x, g prime is e to the x. It's its own derivative. So now I know here I have to put f prime times g plus f times g prime. F prime is this guy, so that's going to give me 3x squared times g is just the original function, e to the x, plus f, which was x cubed, times g prime, which ends up being the same thing, e to the x. You don't have to write this, but I know a lot of students who prefer writing that down, have it just where they just plug it in. It's very fine to jump from here to here. Just know you take the derivative one at a time, right? So first I take the derivative of the x cubed, leave that guy alone, plus leave the x cubed alone, differentiate that guy. Right? And that would actually be your answer. So that is the derivative of that function. Right, so that is the function that gives you the slope of the tangent line at the point x. What is y prime here?
6x.
So you differentiate the first guy, which is 6x times,
1 over x?
no,
Oh, no, we have to put.
Oh.
you put that function back, right? You differentiate one, you leave the other one alone. Plus,
3x squared.
you leave the first one alone that you differentiated before, and then you differentiate that one, which is 1 over x. Right? So this here, it's like that I called my f, this I called my g, and I did f prime times g, and then this is f times g prime. Right? Like I say, you can go to the corner if you don't want to get confused. You can say f is equal to 3x squared, g is equal to ln x. You know that your f prime is equal to 6x, your g prime is equal to 1 over x, and then you plug it into that form. So it's this times that, plus this times that. Right? This you can kind of simplify. X would cancel into that guy. And so you would get 6x ln x plus 3x. Questions on that? So y prime is going to be 1/2 x to the minus 1/2. How do we know that?
You put x as 1/2 instead of the square root.
Right. There's no rule for radicals, so we write it as a power and use the power rule. This just means x to the 1/2. So you bring the power down, subtract 1 from the power. Okay, what else?
Times e to the x plus e to the x squared root x.
Right, so you differentiate the radical x, you leave the e to the x alone. Now, you leave the radical x alone, and you differentiate the e to the x, which happens to be itself. That would be your answer. So that's your f prime times g plus your f times g prime. Right, where that's my f, that's my g.
So in our answer, would you want us to leave it with the radical? Or would it matter if we left with x to the 1/2?
I don't care, either way. It's the kind of thing they torture you with algebra class. In algebra class. Okay. So, how do you do this?
Square root of x plus 1/2 x to the negative.
So you're going to do y prime equals 1/2 x to the minus 1/2 times x. So I guess you're calling this the f and that the g, which is completely fine, but okay. Plus,
Square root of x.
leave the square root x times 1. Would you be able to simplify that? That definitely looks simplifiable. Because this, what is that? That's just x to the 1/2. So this is 1/2 x to the 1/2. Plus, this guy is just x to the 1/2. Right? Which is what? Those are like terms, we can combine them. What would I get? 3 halves x to the 1 half. That kind of looks weird. I wouldn't have used the product rule if I were doing this. I would just realize that this is just x times x to the 1 half. This is just x to the 3 halves. And then I do the power rule. 3 halves x to the 1 half. That power rule. Moral of the story. Don't make things too complicated. And I'm gonna show you more examples like this when I talk about the quotient rule. You're gonna realize not everything you just jump to the product because you see a multiplication. Sometimes simplify first. If you can simplify before taking derivatives, do that. You can always break down from a more complicated rule to a more basic rule if you simplify before. Right? There are a lot of times when, and which is why simplifying is a big deal in our course. Like that's why they ask you questions on the final. Oh, just simplify this for us, because they just want you to know that sometimes when you're given a function in its raw form, it might not be the best form to move forward with. Sometimes you need to simplify, and it can greatly reduce the amount of work you have to do. So a problem like this, these are just powers of x multiplying together. I would just use my laws of exponents, combine them, and do the power rule. I wouldn't think of doing the product rule. In a similar way, if my y was something like 5x cubed, right? Technically, I could have used the product rule here. Technically, I can look at this as a function, a constant function, f, and that is a function, g, right? And I can say, well, you know, my f is 5, so my f prime is going to be 0, and then my g is x cubed, so my g prime is going to be 3x squared. And so then I can take my y prime to be f, well, f prime times g plus f times g prime, and end up with 15x squared. But there's really no point in going through all that, right? The rule is a rule. It will always work. Anything you write as a product and you apply the product rule to it, you will get the right answer. But sometimes it's overkill, right? I just know that this is a constant, so I just leave it alone, differentiate that, get here right away. Right? So sometimes you might not have to go through all the work. If you can simplify before doing something, you just do that and apply a more basic rule. Always look to make your life easier. So just because I say, oh, differentiate this function, doesn't mean you have to use that function. Maybe I just intentionally wrote it ugly just to waste your time. Which actually happens pretty often. That's why it's funny sometimes. You hear students complain, Professor didn't give us much time on that exam. Turns out it's because you're looking at it too complicated. It's like, oh, you're just looking at it this way, and there's like 5 seconds. Instead you took 2 pages and 30 minutes. Because you're being too complicated. Yeah, here's an exercise that we're going to go through together. Find the derivative of this kind of function. I'm going to use that to show you something else. One over g of x, given that g of x is differentiable. And of course not equal to 0. So if I want to find the derivative of the function 1 over g of x, technically we don't know how to do something like that yet, so I'm going to use the definition, limit definition. This means 1 over g of x plus h, minus 1 over g of x all over h. So here I would find the common denominator, which is g of x times g of x plus h, and I'd multiply top and bottom by that. G of x times g of x plus h over g of x times g of x plus h. So this would become g of x minus g of x plus h over h times g of x times g of x plus h. And you might notice I can write it like this. I could write this as minus g of x plus h minus g of x over h times 1 over g of x times g of x plus h. Well, what's this guy? That's the derivative of g. So this is minus g prime of x times, what would this guy become as h goes to 0? Well, this would just become g of x times another g of x. I get g of x squared. So this is 1 over g of x squared. So in other words, the derivative of 1 over g is minus 1 over g squared times g prime. Keep that in mind. Like the proof of the product rule and the proof and things like this, you don't have to know. I just kind of want to show you guys, like all these formulas in your book, they actually come from somewhere. So I'm just kind of showing you all these ideas that happen to come up with these formulas. They weren't just random. You're really just using a definition to figure things out. So here's a problem. Differentiate y equals a derivative, a division of functions. Right? Now, one thing you can note here is that derivatives do not distribute across division. So, for example, the derivative of f over g is not the same as just differentiating this and differentiating that. It's actually not true, right? And again, we can use the derivative of x squared as an example, right? I know the answer should be 2x, but you know what? I can actually write x squared as something like x cubed over x, right? Now, if I differentiate the top, I would get 3x squared, and if I differentiate the bottom, I would get 1, right? Notice that that's 3x squared, which I know is not what the answer should be. So if you have a division, you can't just differentiate the top and differentiate the bottom. It's not going to work, right? So now the idea is, what should work? What is the rule? What is an equivalent to the product rule for quotients? So it's going to be a similar thing. We're going to figure it out, and we're going to use what I just showed you over here. Note, if I say y is equal to f of x over g of x, I can rewrite this as f of x times 1 over g of x. Now, by the product rule, which we already proved, y prime would be, I differentiate this one, leave that one alone, f prime of x times 1 over g, plus, I leave this one alone, and I differentiate that one. What is the derivative of this one? Well, it's that. So this would be minus 1 over g squared times g prime. other words, and this, I can actually create a common denominator and combine these fractions, right? I can multiply this by g over g. So I get f prime times g over g squared minus, this would be f times g prime over g squared. And I can, g squared is a common denominator, I can combine those. F prime times g minus f times g prime over g squared. This leads us to what's called the quotient rule. This says the derivative of a quotient, or a division, is f prime times g minus f times g prime over g squared. This you also have to remember. This is called the quotient rule. Used to differentiate divisions of functions. So it turns out with division, you can't just differentiate each piece and stick it together. That will actually give you the wrong answer. If your functions are, you're dividing one function by another, then the derivative of that kind of function is actually going to be this. The product rule, because there's a plus sign in the middle, it doesn't matter what order you memorize it in, but notice that I wrote it in the same order, right? So you want to take the derivative of f times g, but instead of a plus, you have to have a minus. And you can't switch these terms because you'll get the wrong answer. So it's important that you memorize this in this order. And just to make the product rule easier, I also put it in this order, but there's a plus sign in the middle. There are many mnemonics for remembering this. Some people say it's like, they call this high, they call that the low, because it's on the bottom, and it's like low d high minus high d low over low squared, or some sort of phrase. I literally remember it as a phrase as well. I just say it's like, it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. I literally say that in my head all the time. Yeah, so I did the product rule. So I differentiate this one, I left that one alone. Then I left this one alone, and I differentiate this one. Now I proved before, I erased it now, that the derivative of something that looks like this is that. So I just plugged it in derivative. So now here, this is a fraction, the denominator is g squared. This is also a fraction, but the denominator is g. So I wanted to combine the fractions, so I create the common denominator. Multiply this by g over g to get that g squared. And so I get this and that, which I can combine. You don't really have to know the proof for this. You have to know what's in the box. Like, you have to know that form. I just don't want you to think that formula is so complicated because math people want to ruin your life and make you fail, but it had to be that. We don't like complicated formulas either, but that's what it had to be. Yeah. So yeah, that's called the quotient rule. We use that to differentiate divisions. So let's do some examples. Let's see if it actually works out with x squared, this stupid example that we'd never do this for, but I just want to show you that it's consistent with everything. So I know the answer should be 2x. What if someone decided for whatever reason to write this as x cubed over x and apply that rule? Would you still get 2x as the answer? Well, here, this is my f, that is my g. So what I'm going to do is I'm going to take f prime, that's my f prime, times g, minus f times g prime over g squared, which is x squared. So on top, I would have 3x cubed minus x cubed over x squared. 3x cubed minus x cubed is 2x cubed over x squared. X squared cancels to this. I actually get the answer 2x. Of course, if you get the derivative of x squared, you just use the product rule, the power rule. I just want to show you that even if you broke it up as a division or a product, these rules will still work no matter what. Which is, again, going back to show you, you can make something insanely complicated for no reason. Always try to think simpler. Always try to simplify things as much as possible to fit a rule with very little difficulty. Let's do some more complicated examples, though. Differentiate the following. I think I actually wrote down specific examples here. So my y is equal to x plus 1 over x plus 2. Again, first notice that if I just differentiate the top, I get 1. Differentiate the bottom, I get 1. You get 1 over 1. That's not the answer. This function is a lot more complicated than that. It definitely does not have slope 1. If you look at the graph of this, it doesn't have a constant slope. Okay, so how do we proceed?
1 times x plus 2.
Okay, so in general, we see a division. So we remember our formula in a certain way. I use F and G. Other books might use U and V. It really doesn't matter what letters you use to memorize the rule, but whatever it is, formulate your thing in terms of that rule. So you think of this as F, think of that as G, right? And you know what you want to write down is F prime times G minus F times G prime. And especially if you haven't seen the quotient rule before, every time you're doing a problem with the quotient rule, write the rule down. If you write it down repeatedly, you'd start to remember it. So you know that's where you're headed, right? So first you want to put the F prime. Now this is your F. What's F prime? 1. Right, derivative of x is 1, derivative of 1 is 0. So F prime is 1. So it's 1 times G, x plus 2, minus F. F is the top one. So I'm going to write that down. Parentheses, because I'm after a negative sign. Times G prime. Derivative of x is 1, derivative of 2 is 0. So that's just 1. All over G squared. So this gives me x plus 2 minus x minus 1 over x plus 2 squared. X kills the x, 2 minus 1 is just 1, so this gives me 1 over x plus 2 squared. So I had a division of functions here. And I could do that. probably worth mentioning. I've known people who have moral reservations with the quotient rule. Like, they have an emotional reaction to it. Oh, I probably should do this after I do the chain. Although I did teach you enough to actually understand this, but with the chain rule, it will come by a lot easier, right? So one thing you could do is you could actually rewrite this as x plus 1 times x plus 2 to the minus 1. And you could actually do the product rule, and it would still work, right? Differentiate this, leave that, plus leave this, and differentiate that. This is like a 1 over g. We know that that's going to be minus 1 over g squared times the derivative of g, which is 1. So this gives me 1 over x plus 2 minus x plus 1 over x plus 2 squared. And you'd end up getting the same thing. Plus 2 squared. So it turns out, use the product rule to prove the quotient rule. That's what I did. So at any given time, you actually have a choice of whether you want to even use the quotient rule or not. But usually it's nice to do it that way. So we could use the product rule. By just bringing the bottom up, writing it as a product, and applying the product rule, you get exactly the same answer. And especially if simplifying isn't what you care about, you could get to the answer probably quicker if you would like to stop here. But if you need to simplify, then probably going with the quotient rule straight up would be better. Okay, the second guy, b. X squared over 3. All right, how do we proceed?
2x times 3 minus x squared over 3.
Come again?
2x times 3 minus.
Okay, so you can do the bottom times the derivative of the top minus the top times the derivative of the bottom, which is
0.
all over
3 squared.
the bottom squared. This would give me what? 6x minus 0, which is 6x, over 9, which we can simplify. 3 to this goes 2 times, 3 to that goes 3 times. Now that is true, but I would not have done it that way. Can anyone see an easier way to look at this?
Would you agree to the -1? Better way.
A better way would be to think of this as there's just a constant 1/3 times an x squared. Right? Or yeah, you bring it up, 3 to the minus 1 is the same as 1/3. So there's just a constant times a function here. I would just leave that there, differentiate that. And I get the 2/3. I get the same thing, a lot easier. Right? Very similarly, the next example, C, I said my y was, what did I put, 4 over x cubed?
Yeah.
Right. Similarly here, I would just say, well, this is just the same as 4 times x to the minus 3. Right? That's a constant times a function. So my derivative is, I leave the constant alone, differentiate the function. So it's minus 12 x to the minus 4. Now I could use the quotient rule here, and I would have gotten to that answer, but it would be a lot more work. and a lot more room for error. The moral here, if the numerator, and especially the denominator, is a constant, the quotient rule tends to be a waste of time. And yes, I've seen people use the quotient rule on things where they didn't have to use the quotient rule and they ended up getting the wrong answer. Whereas if I knew if they saw it the other way, they would have gotten the answer pretty easily and correct, right? So something like this, yes, it's a division, but the top is a constant, right? So I can just move this up, think of it as a constant times a function, and apply one of my old rules, right? Similarly, if the bottom is a constant, I can just factor that off and use one of the old rules. You don't always have to use division, quotient rule, right? It takes a little bit more observation, and it's worth it at the end of the day to actually not just generically run into some rule or property, but you actually look at the function and see, is this the best rule to apply? Or can I rewrite this function and use a simpler rule? It can save you a lot of headaches. Right, so if my numerator or denominator is a constant, I wouldn't use the quotient rule, I'd just rewrite it and use the constant factor rule that we did in the last section. What was the other example?
ln x over e to the x.
So I see that, the first thing I'm going to think is, oh, can I simplify that? Turns out I can't, right? So I would just jump into the quotient rule. This here is my f, this here is my g. So I know my y prime is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. F prime is 1 over x, g, e to the x minus f, ln x times derivative of g. It's also e to the x over the g squared, which is e to the x squared. Notice here, e to the x is a common term, I can factor that off. And I can cancel this with that. And so it's like 1 over x ln x over e to the x, which is a complex fraction. It's kind of okay to leave it like that, but I'd probably multiply by x over x to clean it up a little bit. 1 minus x ln x over x e to the x.
But if we left it with,
I don't think I'd care. Yeah, it's worth mentioning. In general, if the whole problem is to find a derivative, unless I ask you to simplify in detail, like I wouldn't care if you do it as something like this or something like that. But usually you'll notice that you'll want to find a derivative in order to do something else with it. So if that's the case, it's to your benefit to simplify it so that when you're plugging it into something else, it's not a headache, right? So it's good practice to learn how to simplify things, but if that's the whole point, then I wouldn't care if you leave it as this or that. If differentiating is the end goal. Usually it won't be. It's just a means to an end. You're using it as a tool to figure something else out. What was this? E to the x ln x? How's that? Wait, can I just simplify? Doesn't this cancel and become x? Why not?
Because the E and the ln is next to each other.
They're next to each other. It is right.
But it's an exponent, no?
Yeah, it's a product. It's not the same, right? You have to remember that e and the ln is in the power. That becomes x. Or there's an ln and the e is on the inside. That becomes x. I did that on purpose just to make sure that you... Right? Little things like that. It matters where things are located. Okay? Don't just think, oh, there's an E and an ln beside each other. You can just kill them. No, you can't. They have to have this particular relationship. The ln has to be in the power of E, or the E has to be inside the ln, right? Having them multiplying each other, an e to the x by an ln x, you can't simplify anything. It's an e to the x times an ln x, right? Which means, how am I going to differentiate it? What rule? Product rule. I have a multiplication of things, so I'm going to take f prime times g plus f times g prime, where this is what I'm calling my f, that is what I'm calling my g. So f prime is just itself, e to the x, g is ln, plus f is e to the x, g prime is the derivative of that, which is 1x. I can factor out the common e to the x if I wish. Does this or that. Okay. So last time we knew some basic rules to differentiate basic functions individually. Now we're figuring out how to differentiate products of functions and quotients of functions. There's one other kind of function we want to be able to differentiate. Composite functions, which leads us to the next section. That's 3.4. 3.4 is another very important differentiation technique. It is called the chain rule. I won't prove this for you. The proof is a little bit subtle at this stage. So I'll basically just break it down for you right now and tell you what the rules are. There are two basic formulations. Basically, the chain rule is used to differentiate composite functions. Right? These are basically functions inside of functions. You know, like an f of a g. Right? Where you take one function, you plug it into another function, and you create a whole new function, differentiate that function. Right? Why would we care? Why make things complicated, Jhevon? I'm just trying to get into med school. You give me all these rules. Like, what are we doing? Here's an exercise. Let's say I wanted to differentiate this guy based on the rules we have so far. How would you differentiate that guy? Yeah, you could do the product rule. You could also, because it's just a square, so yeah, could do product rule. You could say y is equal to x squared plus 1 times x squared plus 1, and then do the product rule. I was thinking a little bit more elementary, but that's one way you could do it. You could also say, because I know how to square a binomial, so I just know it's actually x to the 4th plus 2x squared plus 1. And then I could use the power rule. Right? So that's 4x cubed plus 4x plus 0. Right? So we can differentiate that. No problem. Alright? Here's another example. Differentiate x squared plus 1 to the 20th power. Still want to do the product rule? Still want to multiply out? No, you don't. Right? Yeah, now you panic. No. Now, you need something else. You need a more efficient rule to get around this, right? Sure, you do not want to do the product rule 20 times, even though you could. Neither would you want to multiply out to the 20th power. That's going to give you 21 terms. You spend the entire exam trying to find a derivative. This is where the chain rule comes in. So here's what I'm going to show you now. The trick here, look at this as a composite function. Look at this as something like f of g of x, where your f of x is x to the 20, which we can call the outside function, while your g of x is equal to x squared plus 1, which is the inside function. Notice that if I take this and plug it into that, I get that, right? I can think of it as a composite function. Now, knowing that something is a composite function, there's a rule that I have. I'm not going to prove it for you. I'm going to tell you. We can now use the chain rule. It has two formulations. The first one we'll be using more often, but the second one is useful as well, and we'll use it a lot in future sections. Here's one formulation. The derivative of a composite function, f of g of x, is equal to f prime of g of x times g prime of x. And this is just something we know now. This you have memorized. More like your own name. In other words, differentiate the outside function leaving the inside alone. Right? Leave it intact. Then multiply by the derivative of the inside function. That is called the chain rule. Now with that rule, differentiating something like this becomes trivially easy. So what if I wanted to differentiate x squared plus 1 to the 20th power? Notice that this guy here is my inside function.
Can you do the power rule first?
Yeah. This here, the 20th power, is the outside function. Yes, this is a power function, which we know how we can use the power rule on it. So what this means is that this is going to be equal to, you kind of pretend that the inside is just one variable, you leave it alone, and you differentiate what's going on outside around it, right? So if I had something to the 20, the power rule says I'm going to take that 20 down and then subtract 1 from the power, so now it becomes 19, right? Leave the inside alone, right? That's this part. You're differentiating the outside function, but the g of x stays intact, you don't touch it. Then you would multiply by the derivative of what's inside. Open parentheses just in case, because if there are several terms, you want all of them multiplying it. This would just be 2x. Derivative of 1 is 0, so that's it. And that's actually your answer. I can simplify a little bit. Take the 2x times the 20. I get 40x times x squared plus 1 to the 19. For those of you who are suspicious, let's actually check one where we actually know the answer from before. What if if I ask you the derivative of this guy that we did before with the square? I could do this rule again. Again, the inside is x squared plus 1. The outside is the square function. So I can differentiate the outside, leave the inside alone, times the derivative of the inside, which that's going to give me 2x. Now I can actually multiply this out. This is 4x times x squared plus 1, which gives me 4x cubed plus 4x, which you'll notice that was the answer we got last time. And it was even a little easier. I didn't even have to remember how to expand the square. So that's called the chain rule, used to differentiate composite functions. So if you have a function plugged into another function, the chain rule is who you want to use. There's another way to look at it. Using the Leibniz notation, dy dx is equal to dy du times du dx, where u is kind of your inside function. It's basically the same as the previous rule, except now I'm renaming variables. So we'll use this less often, but it's kind of the same thing. So it's kind of like if I'm given y is equal to x squared plus 1 to the 20, then I can say u is equal to x squared plus 1, which means that my y just looks like u to the 20. So this means dy du is going to be 20u to the 19, while du dx is going to just be the derivative of that. And then I multiply them. dy dx is equal to 20 to the 19 times 2x. And then I just replace my u with that. So for problems like these, it's kind of complicated to use it this way, but there are other ways. There are other times when thinking of that in terms of this formula will be a lot nicer, especially in things like related rates, which we will do in the next chapter. But yeah, by far the first formula is the one we'll be using most of the time if we're doing the chain. Okay. Let's do some examples here. Find the derivatives. Did that? E to the x squared. Now that I gave you all these rules, I can make things really complicated for you to differentiate.
No.
Yeah, do this with the limit definition. That would be fun. Yeah. I could literally put a whole test at one problem.
Oh.
Limit definition. Give you guys an hour. But with the rules, it's actually these aren't going to be that bad. Well, I'm going to reformulate some of our general formulas in terms of the chain rule because it's useful to think of them that way. But after we get through these examples. So you see something like this, you notice that none of our rules really apply to this. I know the derivative of e to the x is e to the x, but e to the x squared is actually a much worse kind of beast, right? But I can think of it as a composite function, right? Where my outside function is e to the x, and then my x squared is like an inside function, right? I take x squared, plug it into e to the x, and I get this. So by the chain rule, notice that here I'm thinking of f of x as e to the x, and my g of x as x squared. If I take this, plug into that, I get that. So my y prime is going to be, what's the derivative of the outside? Derivative of e to the something is just itself. But then I multiply by the derivative of the inside function, which is in this case x squared. So I'm going to multiply by 2x. And that's your answer, 2x e to the x squared. Note, this generalizes. The derivative of e to anything is actually going to be the derivative of that thing times the original function. This is something that we know now. Derivative of e to any power is the derivative of the power times e to the power. Right? So I could make this as complicated as I want. I could say, what is the derivative of e to the x cubed plus e to the x? That's what it's going to be, e to the x cubed plus e to the x times 3x squared plus e to the x. That's the answer. And it applies by the chain rule, right? Differentiate the outside, multiply by derivative the inside. Okay, who's my outside function here? ln is the outside function, ln of x. And the inside function is? Right, x cubed plus 2x plus 1, right? So this here is like my g. And the ln is like my f, ln of whatever. So then this is going to be, y prime is, how do you differentiate ln? It's 1 over x, right? But I'm thinking of this as my x for now. So it's 1 over this whole thing. But by the chain rule now, I have to multiply by the derivative of that whole thing.
3x squared plus 2.
3x squared plus 2. So the derivative is 3x squared plus 2 over x cubed plus 2x plus 1. This generalizes. It is now a rule that we know that the derivative of ln of anything is the derivative of that thing over the thing itself. Example. Nikolai asked me yesterday, too bad he's not here, the derivative of ln of x squared. He's like, well, the derivative of ln x is 1 over x. Is the derivative of ln x squared 2 over x? Turns out the answer is no. Y prime would be 1 over the thing times the derivative of the thing. And what would you get?
2 over x.
2 over x. Right? Which, again, there's another way you can see this. Yes, this is the previous example. In fact, for any constant, you can. What's another way you could have seen that? This same one. Did I have to use the chain rule here? Maybe I could have rewritten this somehow. How can I rewrite that? 2 ln x, right? Now, of course, my x is technically absolute values. I could have negatives and positives here. But now, that's just 2 times the derivative. That's 2 over x. However, if you had y equals, I think this is the one you asked me about. If you had something like that, then your y prime would be 1 over 2x times the derivative of that. The 2's always cancel, you always get 1 over x. In fact, y equals ln of any number times x, as long as this is positive. It's always going to be 1 over x for the derivative. And this general rule, it applies to anything of that sort. So I can ask, what's the derivative of ln of x cubed plus e to the x minus ln x? Well, that's just going to be, you put that thing in the denominator, and in the numerator, you put its derivative. Derivative of x cubed is x squared. Derivative of e to the x is e to the x. Derivative of ln x is 1 over x. So it looks complicated, but the derivative is actually pretty easy once you have that formula at hand. What example am I on? C? How do you differentiate that? Now at this point, resist the urge to think that you can take the radical of each part and just differentiate using the power rule. That would be totally crazy. You get 0. Because that would be a blasphemy.
The outside is radical.
The outside is radical x, right? You can think of this as 2 minus x squared to the 1/2 power. So it's like you take x to the half and you plug inside of it this guy. So as long as you don't just have an x, but you have a whole function, you need to use the chain rule. So for this, I'm going to say y prime is equal to, you differentiate the outside, multiplied by the derivative of the inside. Derivative of 2 is 0, derivative of minus x is minus 1, derivative of minus x squared is minus 2x. That's your answer. Any questions on this so far? So at first glance, this might look like an innocent quotient rule thing, but notice that the bottom has a 16th power of a binomial. You don't want to expand that and do the quotient rule.
Will we first use the chain rule on the denominator and then use the quotient rule, or no?
Well, first and foremost, it is a division. There's one function divided by another one, right? So I'm still going to look at this as my f, that is my g. But it turns out when I'm finding my g prime, I would use the chain rule to find the g prime. So remember that my y prime is bottom times derivative of top minus top times derivative of the bottom, over the bottom squared. So I'm still doing things in that context. My f prime is just the derivative of this, which is 1, times my g, x plus 4 to the 16, minus f, which is x plus 1, times my g prime. Now my g prime is kind of messy. That 16 to the power is really messing things up. But I can just think of that as a composite function. Right? I have my x plus 4 plugged in where an x would have been. So I take 16 times x plus 4. Let me write this somewhere. I have more space. So it's f prime, which is 1, times g, minus f, which is x plus 1, times my g prime, which I'm going to use the chain rule for. So I'm bringing down that 16, leave the inside alone, subtract 1 from the power, that's the power rule to do the outside. Then I'm going to multiply by the derivative of the inside, which is just 1 in this case. All over g squared. So that's x plus 4 to the 32. Double the power. Now at this point we can sort of simplify things. If I look at the top, notice that x plus 4 is a common factor. So to factor this, we can actually pull out the lowest power. So I'm going to pull out x plus 4 to the 15. I will be left over with x plus 4 to the first power minus 16x plus 1 over x plus 4 to the 32nd power. In which case this will cancel into that 15 times. I'll be left with what, 17?
Yeah.
And so the inside here, I have 4 minus 16, that's minus 12, x minus 16x minus 15x over x plus 4 to the 17. Again, it's a division. That's my f, that's my g. So I'm going to think of this as y prime equals bottom times derivative of top minus top times derivative of bottom over the bottom squared. F prime is 1 times g is e to the x cubed minus f, which is x, times, what's my g prime?
E to the x over e to the x cubed.
No. How do you differentiate e to some power?
Oh, times 3x squared.
Times the derivative of the power. So it's the original function times the derivative of the power over this squared. That's e to the 2x cubed. X cubed is a common term in the top, I can factor that out. I would be left over with 1 minus 3x cubed over e to the 2x cubed. This cancels into that. So I have 1 minus 3x cubed over e to the x cubed. Questions on that?
What did the 2x cubed come
E to the x cubed squared is e to the 2x cubed. Laws of exponents, you multiply the powers when you raise one power to it. Came from the quotient rule. There's a g squared. So I have to square x cubed. Squaring x cubed means doubling the power. Two x plus 1 to the 8. And how would I do that?
It's the product rule, but you gotta.
Product rule. There are two functions here being multiplied together. So I know I need to use the product rule. So I call this f and call this g, and I know that means my y prime must be f prime times g plus f times g prime. Okay. So far so good. Now finding the f prime means finding the derivative of this. I don't particularly want to expand something to the 8th power. So how would I find f prime here?
Chain rule.
Chain rule.
8 in parentheses 2x plus 1 to the 7th power times the derivative inside just 2.
So that's my f prime times the g, which is just that guy hanging out. X squared plus 1 to the 5th. Plus, now I'm going to leave my f, 2x plus 1 to the 8th, and I'm going to multiply by g prime. And what would g prime look like?
5 in parentheses x squared plus 1 to the 4th times 2x.
Okay. Now simplify. How would you simplify that? Huh?
Just leave it like
Just leave it like that. What if you had to simplify? What if I actually did simplify? What would you do?
You take out a lot of those.
Just give up. I get most of the credit for this, right?
You take out the constants first.
Well, you can take out a lot of things all at once, but simplifying usually means factoring. So what first thing you're gonna look for is common terms, right? So what is common? There's a 2 in both things. So yeah, I can take out a 2. What else can I take out? There's a 2x plus 1 in both things. So what do I take out?
so x plus 1 to the 7th.
To the 7th, right? When something appears in several places, you always pull out the smaller power. So I can take out 2x plus 1 to the 7th. I also have an x squared plus 1 in both things. What do I pull out? X squared plus 1 to the 4th power. Now you write what's left over. Okay, so the 2 I took out, this thing I took out, and I had 5 factors of this. I took out 4 of them, so there's just 1 factor left. So it's 8 times this. That's all that's left in the first term. Plus, Move on to the second guy. There were 8 of these being multiplied together. I took out 7 of them, which means there's only 1 of them left in here. There's a 5 here. I didn't take out the 5, so he's still here. There's an x squared plus 1 to the 4th. I took out the x squared plus 1 to the 4th, so he's gone. There was a 2. I took out the 2, so he's gone. There's an x. I didn't do anything with an x, so he stays. So now I have 2 times 2x plus 1 to the 7 times x squared plus 1 to the 4th times, this will be 8x squared plus 8. This will be 10x squared plus 5x. So here, 8x squared plus 10x squared gives me 18x squared plus 5x plus 8. That would be it. Two things to worry about here. A lot of the times figuring out, remember I was telling you about properties of derivatives last time, how figuring out when the derivative is positive or negative is going to be important, and a lot of times figuring out when it's 0 is going to be important. So the thing is, a lot of times I want to find derivative, I don't want to stop there. I'm going to want to know when is this 0, when is it positive, when is it negative, right? Now if you want to set this equal to 0 and solve for it, this form is useless, but this form isn't. Because I can set this equal to 0. What does that mean? This is 0, or that is 0, or that is 0. And I can solve my equation, set this equal to 0 and solve it. Like I can't do it here, I would need to simplify it to do it here. Right? So you won't always be able to get away with not simplifying. Another moral of the story. Rules can be mixed and matched. Right? So there are problems where I have to do both the product rule and the chain rule. Or I have to do both the chain rule and the quotient rule. Or I might have to do the product rule and the quotient rule and the chain rule. Or an exponential rule with a product rule. You can mix and match them. The functions can get pretty complicated. So those rules that I put in a box, you really need to know them and be able to see when you need to apply them. And just try to make things as simple as possible. Right? So if you're given a function, don't just accept it as is. First look at it. Can I simplify this somehow before I apply a rule? And if not, you just jump in. But other than that, you kind of not. We'll stop there. That actually finishes 3.4.
So when do you want all this homework? We're going to be handing in 5 sections.
Wait, yeah.
So the test is tomorrow,
Monday.
and so on Thursday, give me the stuff for chapter 2 on Thursday, so 2.3 and 2.4, and the chapter 3 stuff give me on Monday.
Okay.
Really spend time on this and really get to know it well, because when we're moving on to the future sections, we're just going to be applying derivatives, using them as applications for other things. So you really need to be quick with your derivatives.
So then it would be 2.3, 2.4, Thursday, and then 3.1 and 3.4.
So 2.3 and 2.4 due Thursday, 3.1, 3.3, 3.4 due on Monday. Next I plan on doing 3.5 and then go back to 3.2, and that will finish chapter 3. That doesn't finish chapter 3, it finishes everything you will need for the next test. Alright, I will see you guys tomorrow.